Hey, Randy, can we start the second part?
Yep. Can you hear me okay? Can you hear me okay?
Everyone, silence, please. Sorry.
Can you hear me okay?
I think I'm not. I'm not hearing you. The sound is not coming. Can you say something?
Yeah, I am talking
Okay.
and
Okay.
it
Great.
seems,
Okay.
got it? Okay.
Okay, everyone. So let's start the second part of the lecture, please. Okay. Okay, Randy, please.
Okay. One thing I wanted to say that we never got to because we didn't get to the Are Gliders Alive discussion point. I think Maturana and Varela would say no. And it's interesting why they would say no. So they stated that autopoiesis has the necessary and sufficient conditions for um, the generation of all the phenomenology of biology. But they reserved the word alive or life for basically autopoietic systems existing in the physical world. Okay. So one way to think about the first lecture was basically showing a way to understand what an autopoietic system is and how to formalize it and compute with it. And the problem of instantiating a autopoietic system in the physical world is not one that that theory addresses. At any rate, now that we have a tentative theory of the constitution of emergent individuals in the game of life, now what I want to do is turn to how to extend that to include the interaction of such individuals with their environments, in particular behavior. So if autopoiesis is the central idea underlying Maturana and Varela's approach to biology, then structural coupling is the central idea underlying their approach to behavior and cognition. And this quote kind of describes what they mean by structural coupling. It says the continued interactions of a structurally plastic system in an environment with recurrent perturbations will produce a continual selection of the system structure. The structure will determine, on the one hand, the state of the system and its domain of allowable perturbations, and on the other hand, will allow the system to operate in an environment without disintegration. We refer to this process as structural coupling. If we can consider the system's environment also as a structurally plastic system, then the system and the environment will have an interlocked history of structural transformations, selecting each other's trajectories. Arguably, that's not a lot clearer than the definition of autopoiesis, but again, my task is to flesh out this verbal description of structural coupling in a much more precise, rigorous way. Loosely speaking, it's an attempt to understand what's going on in a sequence like this, where a glider is confronting its environment, a non-empty environment. Um, uh, that environment is affecting the glider is affecting the environment. The interaction unfolds over time, over which the glider maintains its identity, but at some point, the glider disintegrates. Okay, it quote unquote dies, and then the interaction ceases. We want to try to capture the structure of this sort of interaction and try to find a way to describe it. So that is where we are headed. Let's start by looking at the effect that a glider's environment has on it. Gliders basically can take two forms, which I'm going to refer to as the wedge and the rocket, just to make it easy to distinguish between these things. Okay, the wedge looks to me like a wedge, right? And the rocket looks like a slightly asymmetric rocket ship. If this cell were also on, it would look more like a rocket ship with fins. Okay, so all possible spatial embeddings of a glider, of which there are 16 times all the translations that you can do to place at different locations in the environment, are basically all just reflections, rotations, and translations of these two basic forms. Okay. Whenever we single out a glider, which we're doing now by uh, defining this particular persistent closed organization, we essentially leave behind a glider-shaped hole in the universe. And the interface between the glider and that surrounding universe, which I've denoted here in yellow, is I'm going to refer to as its one environment. It's the non-glider cells that are adjacent to the glider and through which all interactions between the glider and the environment must pass. Okay. That one environment consists of 24 cells, and so we have 2 to the 24, or around 17 million possible states that one environment can take on. In fact, it turns out because gliders move, we sometimes have to consider not just the one environment, but also the two environment, which is the next surrounding ring of cells, for a total of 2 to the 56th possible environmental states. I'm mostly going to skip that detail here, but everything I say can be extended to incorporate not just the one environment, but the 1-2 environment. So we can think of these environment states as perturbations to a glider. And those perturbations can be divided into two subsets. Some perturbations are destructive. This is an example of one. This is a particular one environment configuration that causes the glider to disintegrate, so that after this interaction takes place, there is no longer a glider, and therefore no longer a glider environment. There's just the Conway physics or the Conway chemistry. That's a destructive perturbation. We can also have non-destructive perturbation. So here's another one environment configuration that the glider survives. It's changed by the interaction, and the environment is changed by the interaction, but the glider's identity persists. So we call this a non-destructive interaction. It may change the structure of the glider, but it doesn't change its organization. Its organization as a closed network of process dependencies is preserved. So one thing we can do, and originally I did it exactly this way, is we can exhaustively subject a wedge or a rocket to all 2 to the 24 possible one environment perturbations and look at what happens. Okay. When we do that, we find that the vast majority of one environment perturbations destroys a glider. A glider is somewhat fragile. However, there are 93,788 non-destructive perturbations for the one environment. And somewhat surprisingly, all of those almost 100,000 non-destructive perturbations can be partitioned into only 6 equivalence classes based on what they do to the original glider. So for example, if we take a wedge and expose it to one of these classes of perturbation, it produces a rocket in a particular configuration relative to the original wedge. So if we rotate the wedge 90 degrees to the left, the corresponding rocket would also be rotated 90 degrees to the left. But there are only 6 of these possibilities, 6 equivalence classes. And in order to make these easy to visualize and refer to, I'm going to arbitrarily color them separately. So I'm going to assign a color to each of these equivalence classes. The colors mean nothing. They just let us refer to them in a visually simple way. So a wedge has 4 non-destructive equivalence classes: black, blue, brown, and orange. And a rocket has 2 non-destructive equivalence classes, a gray and a green. And if you look at just if you just gather statistics of gliders interacting with their environment over long periods of time, what you'll see is that the density, the fraction of interactions that fall into these distant classes is quite non-uniform. So the majority of non-destructive interactions are blue, then gray, then black, then brown, orange, and green. And this is something we can explain based on what I'm going to be, this theory of interaction I'm putting together, but I'm not going to go through those details. I don't have time for that here. Interestingly, it also turns out that these same 6 classes persist if we consider the full 1-2 environment perturbations rather than just the one environment. That doesn't introduce any new classes. Okay, so we have these 6 equivalence classes of perturbations, and we can fully characterize these classes. Again, I won't go into the details here, but we can literally compute them. So for example, what did I say? The brown class right here. These cells always have to be off for every one environment in the brown class. This cell has to be off. This one has to be on. These yellow cells can be anything, and these green cells are partially constrained, and you can derive a set of equations that describe those constraints and solve them. And by taking this structure into account, as well as solving that set of constraint equations for the green cells, we can compute that there are 8,192 brown one environments. Okay? And likewise, we can do that for all the other possibilities, the black, blue, orange, green, and gray. Okay? We can enumerate every member of each of these classes from that construction, and we can also explain how each class of perturbations is grounded in the glider organization, which we derived in the previous lecture. Again, I'm not going to go through all of that, but those things can be done. So we're generally not interested in only single glider perturbations. If a glider persists in its environment, it's going to be subjected to a sequence of perturbations as it repeatedly confronts its environment until, again, it disintegrates. So that produces a kind of a tree of possibilities. If we start with a wedge form in this shape, depending upon which perturbation it receives that's non-destructive, it's going to go down different branches, and then the resulting configuration can receive different perturbations. We go down different branches. There is a contingent structure to the way the sequence of glider configurations unfolds over time, depending upon the kinds of perturbations that it receives from its environment. And we can ask not only what is the structure of each class of perturbations, but what's the structure of all possible sequences of non-destructive perturbations. We can map that out. This is this is a representation of the structure of that unfolding for a one cell spatial offset. I'll explain that in a minute. So each node in this graph, which I'm going to call the glider interaction graph, if we expand a part of it, each node corresponds to some particular glider configuration, and each transition between nodes corresponds to some particular class of perturbations. Any one environment that falls into the blue class will initiate that transition starting from this particular glider. Okay, and we see all the different colors for the 6 classes showing up. Okay, so this is the one-step structure of what all possible environment interactions a glider can have will do to that glider. Okay? But again, as I said earlier, it's not just the one-step interactions. We also want 2-step and 3-step, and basically we want the entire sequence of interactions. So we can extend this characterization. This is all the 2-step interactions. That involve the glider moving 2 cells in spatial offset. And what I've done here is I've shown in red the 1 spatial offset graph. So that's this one embedded in the 2 spatial offset graph. And we can keep doing this. We can go to 3 cell spatial offsets. And this red network is this one embedded in the larger thing. So what you see is there's a lot of repeating structure, which ultimately comes down to this one-step perturbation network. But this continues to basically fill the entire universe. So if we have an infinite universe, then this interaction graph is going to be an infinite structure as it unfolds. If we have a finite universe, so for example, if we impose periodic boundary conditions, so there's only a finite number of places you can be, then eventually this interaction graph will also fold up into some sort of a toroidal structure that represents all the possibilities. Now this structure that I'm calling the glider interaction graph is precisely what Maturana and Varela call the cognitive domain, which they define as the domain of all interactions in which an autopoietic system can enter without loss of identity. Okay. Any interaction that falls outside of this graph corresponds to the disintegration of a glider. It involves a destructive perturbation to that glider. So this captures the structure of all of the non-destructive perturbations. Now, clearly one can quibble with their use of the notion of cognitive in this sense, and that's actually one of my discussion questions. I don't want to engage in that philosophical debate here. I just want to emphasize that we can construct these interaction graphs, and these interaction graphs capture precisely what Maturana and Varela call the cognitive domain. Okay? Now, these interaction graphs can get quite unwieldy, even in finite environments, if the universe is large. And as I mentioned, it's got a core repeating structure. So one thing that we can do is take these huge interaction graphs and basically reduce them up to symmetries. So there are different ways we can do that depending upon what symmetries we divide out. This shows the glider interaction graph if we divide out all the translation symmetries. So we still see the 16 rotation and reflection configurations being preserved, but the translation symmetries have been removed. Okay, so we don't say where this particular configuration of a wedge is in the universe. It's just in that configuration. Okay. We can go further if we want. We can also divide out all symmetries, including the rotation and reflection symmetries. And that leaves us with just a two-element graph, one for the wedge configuration and one for the rocket configuration, without any consideration of how it's spatially embedded in the universe. Okay. The most interesting thing to observe about this embedding, because I'm not going to use this one further, but this one is the one we're going to be using. But one interesting thing we can see about this embedding, this symmetry reduced interaction graph, is that although there are many possible embeddings of a glider, there are really only two intrinsic states. And those states basically correspond to whether these two cells are on-off or off-on. That's the only thing that distinguishes a glider wedge from a glider rocket. And if we've removed all embedding structure, all spatial embedding, by dividing out all symmetries, then that's the only intrinsic state. On the one hand, that means a glider is very simple. It can maintain only essentially a single bit of state. On the other hand, it emphasizes that glider is not a purely reactive entity. How it responds depends not only on how the environment acts on it, but also its own intrinsic state. So again, this is arguably the minimal example of a biological individual, as defined in the previous lecture, that can engage in non-trivial interactions with its environment because it has this one bit of internal state. Okay? Clearly, a richer agent would have, I'm going to use the word agent loosely here, the more careful word would be entity or individual, but a richer one would have many more internal states that could be used to color their responses to environmental perturbations. But this one has at least one. Okay. All right. So now that we have this notion of a glider interaction graph or a cognitive domain in Maturana and Varela's terms, now we can go back to this question that I started the structural coupling slide with. How do we understand, how do we think about sequences of natural behavior? And by natural, what I mean is we're not imposing a selected perturbation on a glider and asking what happens, and then we impose another one. We're basically putting it in a non-empty environment and letting both the glider and the environment state evolve according to the Conway physics and look at what consequences that has. Okay, so the perturbation it receives here or here, let's say it this way, the perturbation it receives here is not independent from the perturbation it receives here, because this perturbation represents the Conway physics unfolding of these environmental states, as well as whatever effect the glider had on those states. And likewise, the configuration of the glider here is not independent of its configuration or perturbations here. So now we're looking at, you just plop a glider in a universe, and then from then on, it's hands off. You let the physics dictate what happens to the glider and what happens to the universe. Okay, and this shows one example that I showed earlier of a sequence, which I'm going to fancifully call a glider life, which consists of a blue perturbation, a brown, a gray, two more blue perturbations, and then finally a destructive perturbation that causes the glider to disintegrate. The physics moves on, but the biology has stopped here because the glider organization has been violated. It's no longer present in the ephemeral chemical networks that underlie the subsequent dynamics here. Okay. So we can think of this as a typical agent-environment interaction, okay, where the glider is perturbed by the environment and the glider perturbs the environment. So whatever happens between these two pairs is co-determined by the glider and its environment. Okay. I'm going to do what I always do when I am faced with this sort of a brain-body environment or agent environment system, is that I pull it apart and I ask, what does, in this case, the glider, what is all the things a glider can possibly do as a function of the perturbation it receives? And we've already answered that question. It's basically the glider interaction graph, gives us what's formally the non-autonomous dynamics of this half of the agent-environment interaction. Okay? But this half is an analogous question. What are all the possible non-autonomous dynamics of the environment as a function of the perturbations it receives from a glider? Okay, so we also need to do something like the environment interaction graph. And only once we have the analog of this done for the environment, can we actually understand how these two pieces fit together to generate sequences of non-destructive perturbations like this. Okay, so that's our next task, is to do the same thing we did here for the environments. All right, I'm going to do this as I always do, starting super simple and working up to more complicated cases. The simplest game of life universe that contains a glider is going to be a 5x5 universe, okay? And in a 5x5 universe, there are only 3 environment cells because the glider takes up all of the other cells in such an environment. So this partially includes the full 1 environment. It doesn't fully include it. And to keep things finite, I'm going to assume periodic boundary conditions. So I'm going to fold this 5x5 environment into a torus, where if you go off the left side, you come back on the right side. If you go off the bottom, you come back on the top. Okay? You don't have to do that, but if you don't, then you end up with potentially infinite environments and therefore potentially infinite environment interaction graphs. Okay, so there are only 3 environment cells, but if you work out all possible environment transition states depending upon what's in here, namely a wedge or a rocket, this is the environment interaction graph that you end up with. It has 100 nodes and 400 edges. And each node corresponds to an environment configuration, and each edge corresponds to a glider perturbation. And the color convention here is that if this perturbation was from a wedge, it's colored red, and if the perturbation was from a rocket, it's colored green. The reason this thing is so big is that there are lots of symmetries in this environment. Okay, this doesn't divide out those symmetries. So this is the raw spatial positions in which the glider and the cells could be. These 2 cells could be down here. This cell could be down here. Okay, they could be shifted to the right 1 cell. They could be shifted to the right 2 cells until they come all the way back around. So there's a whole bunch of distinct embeddings of this environment and glider, and that's all of them is why this thing is so large. If you divide out all of the symmetries like we did for the glider, then this collapses to a much smaller graph. So that's the basic idea of characterizing environment interaction graphs. Of course, there's not one environment interaction graph. There's one for each size of universe. So if we extend this to a 6x6 universe, now we capture more of the 1 environment cells that can fit in to that universe, but not the entire 1 environment. We're missing these cells and these cells. Okay. And when we do that, we have 14 environment cells now. So we have 2 to the 14th possible states of this environment. That leads to a graph with over 27,000 nodes and over 17,000 edges. And this is going to be a pretty common theme in Game of Life. That graph is disconnected. So it's got distinct components, over 10,000 distinct components that group into these 6 isomorphism classes. Okay. And each of these have multiplicities. So again, there are different ways that the same graph can show up. Even though the details here are different, you still see the same isomorphic structure. And then there are the symmetry equivalent embeddings. Okay, so for example, there are 25 different examples of a node that goes from one environment configuration to the other via a wedge perturbation. And there are 288 symmetry equivalent ways of generating each of those graphs. So there are 25 times 288 instances of that particular component of this disconnected graph. Okay? But we can map it all out. Let's push this further. In a 7x7 universe, it's the first universe which we can completely capture all 24 independent environment cells. And we also start to capture some of the 2 environment cells. Okay. Now there are 27 environment cells, so there are 2 to the 27th possible perturbations or states of the environment that this universe can have. And this is the smallest universe that completely contains a one environment. The environment interaction graph for this case has over 213 million states to it, or nodes in the graph, and over almost 134 million edges. And it splits up into almost 81 million distinct components, only 2 of which I'm showing here. Okay, so this ... has roughly 81 million other configurations, which you can enumerate. And you also have duplicates and symmetry equivalent cases. So that's what the numbers below are. And that's where my patience ended. So I didn't go any higher than that. It obviously becomes computationally very expensive to do so. But we have now 3 examples of environment interaction graphs that we can experiment with. And as I will show you, that actually is already rich enough to do some interesting things. Okay? All right, so now we're ready to finally tackle structural coupling. So essentially, structural coupling involves the co-determination of paths through these 2 interaction graphs when they're coupled. So when every glider movement in every glider change in configuration triggers an environment change in configuration, and every environment change in configuration triggers a glider change in configuration. Okay, and those two interaction graphs co-determine, again, what I've been calling glider lives. All of the sequences of non-destructive perturbations that a glider might experience in a given universe. Okay, so let's look at how that works. This is a subset of a glider interaction graph. Okay, it's not a full one, but it actually is a true component of the glider interaction graph. And this is a subset of a 7x7 universe environment interaction graph. Okay, and how this works is basically the following. Let's distinguish some initial states. So suppose the glider is in this configuration, in this location, and the environment is in this configuration. Okay. Well, this environment selects from all the possible non-destructive futures of this glider. There are 4. It selects a particular one. Okay. It selects the blue one, causing the glider to go from this state to this state. Okay. Likewise, if I step back for a minute here, likewise, this glider configuration, namely the fact that it's a wedge in a certain orientation and chirality, selects from this environment's possible futures. There's only one here, but that's not always true. There's a branch here. Okay. It selects one, namely this one. So the glider transitions from here to here based on its own intrinsic state and the perturbation it receives from the environment. The environment transitions from here to here based on its own intrinsic state and the perturbation it receives from the glider. And now we've seen a glider life essentially that evolves from here to here. This process just continues. Okay. Here, we've gone one step further with the glider selecting an environment transition and the environment selecting a glider transition. And now we've come to a branch point. Okay. Depending upon what form the glider is, this environment could transition this way if it's a wedge or that way if it's a rocket. Likewise, there are a couple of different possibilities that this glider could transition depending upon the environment in which it finds itself. Okay. Given this environment and this configuration of glider, these are the transitions that take place. The environment undergoes a green transition here and forest green, I should be clear, because there's also bright green transitions for the glider interaction graph. And the glider undergoes a gray transition. Okay. Now we're in state. Why didn't that? Okay, why isn't that up? Okay, I've got a problem, I guess, with my slide build. Anyway, this should persist, G0, G1, G2, G3, but for some reason it's not showing up. Anyway, at time 3, we're in this situation. We're in this glider configuration, and we're in this environment configuration, okay? There are a bunch of different ways, namely 4, that this glider could evolve if it occurred in the right environment, okay? But it turns out that none of those classes correspond to the actual environment that this glider finds itself. So we end up with the glider not being able to make any transition, and since the environment is only defined with respect to the glider, the environment can't make any transition at all. The glider disintegrates, and this glider life ends. Okay, so as long as the glider persists, structural coupling essentially involves the co-selection of future environment states and glider states. But once the glider disintegrates, the separation between a glider and its environment disintegrates. All we're left with is physics and that glider life. And also, if you want to look at it that way, that environment life. It's not autopoietic, so we won't think of it as life, but it's still the existence of the environment defined by the existence of the glider also ends. And both of these chains terminate. Okay? Thus, we see how a particular glider life can be carved out of a glider interaction graph and an environment interaction graph through structural coupling between the two. Okay? Now, once we have this notion of a glider life, that is a sequence of non-destructive perturbations that typically will ultimately be terminated by a destructive perturbation, we can ask another question, which is, what are the possible structures of glider lives in universes of various sizes? Okay? And I won't go through the details, but we can compute those as well. It turns out that in a 5x5 universe, the smaller universe in which a glider can exist as a distinct entity, basically the graph of glider lives just consists of 20 copies of this ring, which is basically an immortal life. The glider just keeps walking through the environment, going around and around the periodic boundary conditions. And it can do that in 20 different ways, depending upon how it's embedded. Or if you divide out all the symmetries, there's basically just one immortal life that can occur in a 5x5 universe. In a 6x6 universe, we have 24 immortal lives, and then we have 4 new isomorphic structures, each of which have many different instantiations of terminal lives. In this case, all the lives are short and brutal, okay? You basically live for one step and then you die. Or you persist indefinitely in one of these immortal lives. And notice the immortal lives have gained some transient structure. So you may go through several non-immortal like transitions, but rather than dying the way you do here, you eventually get into this immortal, one of these immortal lives, and you just keep cycling around forever. Okay. So there are a total of 10,680 components to this graph of all the possible glider lives in a 6x6 universe, and they split up into 5 classes, as I've shown you here. In the 7x7 case, we have 212 odd components to our graph of glider lives. They break up into 392 classes, only 4 of which I'm showing you here. And those include an immortal glider with now a much richer transient structure to it before it settles down into its immortal life, a bunch of much richer terminal lives. And interestingly, another thing that can occur is a double immortal glider life. So there are 2 gliders in this universe that just cycle around forever, never interacting because the universe is big enough to accommodate both of them. Okay. And that's, I mean, I haven't gone to above 7x7 as I mentioned, but there are some general things we can conclude here. As the universes get bigger, the lengths of the terminal lives get longer, and their structure gets much, much richer. And for the immortal lives, their transients get longer. So you would expect if we went to an 8x8, you'd still have a bunch of single glider immortal lives, but this structure would, since it went from there to there, you would expect it to become now much, much richer. And you would expect this double glider immortal life, the immortal lives, to gain more structure along these lines. And once you get large enough, 8x8 may or may not be enough, but let's say 9x9 or 10x10, you could support 3 immortal glider lives. And so you would generate more of these cycles and vastly more longer and more highly structured terminal lives. So it gives us at least a glimpse into how this works. But because in larger universes, the environment interaction graph gets larger and larger, unlike the glider interaction graph, we can only take this so far as a practical matter. But I couldn't resist doing one other thing, which is only possible in the 5x5 universe. We can look not at all of the possible glider lives, but we can look at all the possible histories of the entire universe. Okay, so we have 5x5 is 25 cells, so there are 2 to the 25 possible states. We can look at every possible next state that can occur from all of those 2 to the 25 initial states, and we can put them together into graphs. And what we find is that the graph of all possible histories of the entire 5x5 Game of Life universe has over 33 million vertices. It breaks into a forest of distinct graphs. There are over 5,000 of them, and they group into 55 groups with the given multiplicities here according to the isomorphisms and the symmetries. Okay. So basically, each of these components consists of all of the states of a 5x5 universe that fall into the same periodic attractor. So this huge one, which is just a solid blue circle because it has, let's see, it has over 23 million vertices in it. This is the basin of attraction of the vacuum state. These are all the configurations that eventually fall into an empty universe. These other ones fall into more complicated kinds of universes. And in this representation of all possible histories of the 5x5 universe, this little red circle right here is all the glider lives that can occur. Those 20 immortal glider lives are right here. No other glider lives occur in any other possible history of this 5x5 universe. And notice there are these long transient structures, which because we know that there are no glider transients into these immortal lives from our previous analysis, these all correspond to essentially physics and chemistry transitions that eventually give rise to a glider that is then immortal as it just cycles around the universe. Okay. So why did I do this? Well, I think it highlights an interesting point. There are at least two different ways we can think about the situation here. Up to this point, we focused on the gliders and their environments and their interactions, and we focused only on this subset, okay? But an equally valid description would be the description of physics or chemistry, where things like gliders don't exist per se. There's just the unfolding of that single universal law of the Conway physics, okay? Everything that a glider does when we focus on its biology or its interaction with its environment is just at this level of description, the unfolding of the underlying chemistry. So we can flip as observers between these different perspectives of essentially reifying particular structures like autopoietic networks of process dependencies, and therefore limit ourselves to only histories of the universe where such things exist, or we can look at the underlying physics or chemistry. Even in the case where gliders exist, there's still a story to be told at the underlying physics and chemistry. Okay, so where does that leave us? Let me just summarize what we've done. We've defined a glider interaction graph. We've defined a environment interaction graph. We showed that you can put those two things together via structural coupling to generate all the glider lives. And I've also shown how those glider lives are embedded in just the history of the universe. Okay, so this is sort of a classic agent environment interaction graph of the sort I've typically studied at a much richer level, where the agent is not a glider, it's a presupposed body structure that contains a nervous system that interacts with an environment. Okay. So now we have these two things. We have a theory of constitution, which I showed you in the previous lecture, and we have a theory of interaction, which I've sketched in this lecture. The next question we can ask is, what is the relationship between these two theories? Are they fundamentally independent, separate theories, or do they have some interesting connections? And this is closely related to a topic of debate in the interaction literature, which is often referred to as life-mind continuity. Although I'm not going to get into that, it's largely a philosophical debate. It amounts to this. What is the relationship between say, autopoiesis and structural coupling? What is the relationship between life, biology, and mind, cognition? Okay. Here we're not looking at anything that quite that grandiose. We're looking at two fairly well specified theories, one of constitution, where our theoretical object is a generalized glider organization, and one of interaction, where our theoretical object is the glider interaction graph, or if you prefer Maturana and Varela's term, the cognitive domain. And we just want to investigate the relationship between these two. Okay. So again, skipping lots of details, what we showed several years ago is you can do the following operations on these graphs. You can take this dependency graph, which has no global spatial information in it. It has little atoms of geometry in each of the processes, and it has these interdependencies. And you can algorithmically embed that non-spatial dependency graph into space. That can be done algorithmically. We gave an algorithm in this paper. Okay. What that gives us are particular spatial organizations of these processes, which I'll show you what we can do with in addition. But this graph is just this graph, except we've imposed space on it. Or, I'm sorry, we didn't impose it, we extracted all of the spatial structure that's implicit in this dependency graph. Okay? That's step one, spatial embedding, purely algorithmic. The next step is to just color these bundles of process dependencies according to the symmetries of the underlying generalized glider organization. Okay, you could pick any sets of colors. I picked some that are suggestive, as you'll see why in a minute, but I could have picked any color for the blue here, but I would have used the same color for all four of these bundles because of the symmetries. The graph exhibits symmetry. So if I treat this bundle in a particular way by coloring it a certain way, I have to do this and this bundle the same way. Same with all the other colors. Okay. So that's also completely algorithmic. You can pick any color bundles you want, but if you have the graph, the structure that we've extracted with the spatial embedding, and you can determine the symmetries of that graph, then you would come up with an isomorphic coloring to this one. Okay. The next step is that we can take each of these sets of processes and say what configuration of components in space would be necessary to produce that set of processes. That's also a purely automatic operation that you can perform. And we just replace each process set with the corresponding configuration of components that would trigger that set of processes. Finally, I hope everybody can see where I'm going here, I can take all these bundles of dependencies, which are now redundant because they interconnected different processes which no longer exist in this representation, and I can collapse them all to a single link. And when I do that, when I group those, again, that's a purely automatic process, I end up with this graph. That graph should look familiar. It's just this graph. So what I've shown you is that starting from the generalized glider organization, you can purely automatically derive the glider interaction graph from its organization. Although I originally computed this thing independently by subjecting a glider to all possible perturbations and then recording what happened, that's not necessary. Okay? Once you have the generalized glider organization, not the vacuum, but the generalized glider organization, you can extract or derive the interaction graph from it. Okay? So what that means is that consistent bundles of process dependencies over in the generalized glider organization graph correspond to these classes of environmentally triggered transitions in the glider interaction graph. Okay. We've derived the cognitive domain rather than measuring it. So that's kind of cool. That was not something I thought would be possible ahead of time, but we were able to do it. So where does that leave us? We have this theory of constitution, which started as the vacuum glider organization, and then we generalized it to the generalized glider organization. We have this theory of interaction, which involves the glider interaction graph and the environment interaction graph, putting them together via structural coupling to produce glider lives. And now I've shown you that you can derive the glider interaction graph from the generalized glider organization. Okay. Notice this is not the same thing as you can completely derive behavior or cognition or mind, or whatever term you want to use on the right-hand side of that life equals cognition. You cannot derive it completely from just the biology. Okay. This depends on both the glider interaction graph and the environment interaction graph. And the environment interaction graph is not something you can derive from the generalized glider organization. The generalized glider organization partitions the universe into glider and not glider, and then the physics and chemistry of the not glider part is what determine the environment interaction graph. And it's only when you put those two things together that you get, through structural coupling, that you get the full glider lives. Okay, so we've partly derived, again, scare quotes, okay, mind, behavior, cognition, whatever is on the right-hand side of that life equals cognition equation. We've partly derived it from life, but we haven't completely reduced it to biology. Okay, which gives us, I think, a much richer view of the relationship between constitution and interaction that simple-minded life equals cognition catchphrase that's bandied about does. Okay, I have, where am I at? Doing pretty well. Okay, I have one more thing I want to show you, and this is kind of speculative, but I think it's an interesting speculation, and then a good place to go into my wrap-up. And then we will be ready for questions and discussion. Okay. I hinted at this earlier. I made the point that we can take different perspectives on the game of life universe. Okay. One perspective is that of physics. It's just once you have the grid, the binary grid, and the law, the Conway physics law, then everything else is determined. Okay. And that is as objective a perspective as we can take on the game of life. There's no interpretation whatsoever. It's just given by the physics. Okay. But that's not mostly what we've been doing. What we've mostly been doing is basically standing outside that physics and selecting out, as Daniel and I were discussing earlier, particular entities of interest, like a glider, in part because our pattern matching abilities tend to like compact, localized, persistent entities. They tend to lock onto things that aren't completely transient and completely distributed across the entire universe. Okay, so that's why we pick out entities like the glider. And then, from our perspective as an external observer on this game of life universe, we've characterized the defining structures that correspond to that glider or other entities. We've picked out the environments that surround it as another theoretically important object. We've characterized the dynamics of those environments. We've characterized the dynamics of interactions and so on. That is, I mean, this is what I meant by we're playing scientist. Okay, we're playing scientist on this universe determined by the game of life rather than the other universe that we're embedded in. And that's helpful because one of the problems that we run into, as Daniel mentioned, is a circularity when we try to play scientist on this universe that we are in, because we are a part of that universe. And our operations as scientific observers are crucial to science because we select out the entities that need to be explained. Okay? We select out the kinds of explanations that we're willing to accept. So us as scientific observers play an important role in carrying out science in the real world, but we're also a part of the real world and ultimately a part of what we need science to explain. The situation's a little different in the game of life. We are playing scientist as true objective observer. Well, we have to be careful about objective. You could argue that an alien with a very different perceptual system might not pick out the same kind of structures that we do in the game of life universe. Okay, so there is a component of subjectivity, but at least it's not circular because we are not a part of the game of life universe. And breaking that circularity is, I think, one of the key useful things about this entire research program that I've been talking about, is it lets us make a certain amount of progress on understanding how biology might be related to physics and chemistry, and how behavior and potentially cognition might be related to biology without getting trapped in these loops of circularity. But it leaves out the other half that the real world captures, which is we want to explain how observers like us actually work. Okay. And what I want to suggest is we might actually be able to make a little bit of progress on that if we recognize the following thing. Although we stand outside the game of life universe, there are entities within the game of life universe, like the glider, that has their own perspective on that universe. We peer in and we see the raw physics, or if we adjust our microscope a little bit, or our telescope, we see these entities interacting with their environments. A glider doesn't see any of that. The only thing a glider can do is distinguish these 6 possible environment configurations and the way that those play out over time. So a glider has its own perspective on the universe, which is different from our perspective, and it's different from the actual physical structure of the universe. These classes that I've completely mapped out and explained how they're grounded in the glider organization, they don't matter to us. The things that are blue versus the things that are orange in these one environment classes don't make any sense to us in terms of our perceptual classifications. They also aren't intrinsic to the glider universe. They only make sense to a glider. Effectively, they are what von Uexküll called the glider's Umwelt. It's the world as experienced by a glider, as distinct from the world as experienced by some other entity in it or by us outside of it. And it suggests that we might be able to, from our external perspective, be able to start developing theories of subjectivity by taking advantage of the separation. We have an objective observer and we have the beginnings of a subjective observer, but unlike in the real world, they aren't one and the same. The objective scientific observer stands outside of the universe. The subjective observer is a construction of this universe that we can try to explain, try to understand. Okay, so that's purely a speculation, but it might be a fun place to start thinking about an account, essentially an objective account of subjectivity. Okay. All right. On that provocative note, let me summarize and then I will wrap up. Again, I think I'm pretty much on track, which is great. So going back to the original research strategy that I mentioned I was going to undertake here, um, starting with this question of what is an agent and on what basis do we distinguish an agent from its environment? And how does that play into the way in which we investigate its behavior and potentially cognition? And I put forward this basic strategy where we first select a theoretical framework, an initial guess as to what a useful set of ideas that we might want to try and apply to that question. For us, that was Maturana and Varela's biology of cognition. Again, I want to stress that other people could select different theoretical frameworks. I more care about the overall pattern of investigation here that I'd like to show you the benefits of, rather than necessarily convincing you that Maturana and Varela's biology of cognition is the one true way. I do think it has a lot to recommend it, but it also has a lot of limitations and puzzles that persist. Then I picked a toy model in which I could investigate the application of their conceptual framework. And I picked the game of life model universe. And I think there are interesting arguments that recommend that particular choice. But again, one could pick a different toy model universe that, for example, has thermodynamics in it, that requires non-equilibrium situations in order to have persistent entities develop, that isn't discrete in time or discrete in space or discrete in state. You could make other choices there. I'm not insisting that my choice is the best one, but it is a choice. Okay. Then I've basically showed that using the terms of that theoretical framework, Maturana and Varela's biology of cognition, applied to this toy model, we can actually build some interesting non-trivial theories. One of constitution, one of a kind of biology, and one of interaction or a kind of behavior / cognition of emergent individuals. And those theories are well enough worked out because we've specified a simpler toy model universe to explore it in, that we can actually compute a bunch of interesting things from that theory. So we can compute organizations. We can derive intrinsic viability constraints or answer some questions about origins. Those are great because I didn't give you the details of that. We can calculate the non-destructive perturbation classes. We can calculate the natural perturbation statistics. Again, I didn't show you that. I just gave you the result. But those can actually be calculated from the theories. We can derive interaction graphs or cognitive domains, as Maturana and Varela call it, and we can understand how lives get constructed in this model universe via structural coupling. Furthermore, I've been through actually 2 cycles of refinement. The first cycle was that I started through this path using the vacuum organization, but that ran into limitations, and I eventually had to go back and extend the theory of constitution to the generalized glider organization. Likewise, for interaction, I started with an independently constructed interaction theory. And I only later showed how we could derive that interaction theory as a consequence from the generalized theory of constitution. Okay? So I think this is a particular instance of the overall research strategy that I started out with. Again, you can quibble with every piece of the particulars that I did, but I do think this research strategy has something to recommend it when you're grappling with sort of fundamental conceptual questions in a field like biology. Okay, then to finish, the way I did it was I took these 4 steps. We went from a physics to a chemistry to a biology to behavior / cognition. Again, that's a discussion topic, depending on whether or not you buy Maturana and Varela's notion of cognition. Okay, but I've shown you in some detail how all of this works. And one cool thing, another thing that I didn't get to in the discussion topic, I had a question about why start with physics rather than start with biology. Okay. Every previous model of autopoiesis did that, including Varela's original model of autopoiesis that he developed with Uribe and Maturana. You start with some particular set of processes. You start with some particular set of components, and you basically cut your modeling off at that point. You postulate, essentially, what you need to make a closed network. And the thing I don't like about that is that you're already presupposing the utility of the concepts that you're actually exploring. Okay. Whereas if you start with chemistry or even physics, let's say just chemistry for now, then whether or not those kinds of networks that autopoiesis postulates as being important, whether or not they arise and under what conditions they arise becomes an interesting question for investigation. If you impose them a priori, there's no question about that. Okay. That's a reason for starting with chemistry and having biology be a derived and emergent thing. The reason why I like starting with physics is that even chemistries can be pretty arbitrary. You have to come up with a set of reactions in your chemistry, and you typically would select reactions that are biased towards the things that you're trying to do, like generate closed reaction networks. If you start with a physics, everything else that happens, all the chemistry, all the biology, all the behavior, it's all ultimately a property that comes from the physics. So you're postulating one arbitrary thing, which is, say, the Conway law, and everything else is not arbitrary. Everything else derives from the operation of that law. Whereas if I start with chemistry or biology, you're postulating a whole bunch of arbitrary things, any one of which may be the crucial ingredient. Okay, anyway, last statement, and then I'm done. I haven't talked about inaction, but as I pointed out early on, there's a close relationship between the biology of cognition and inaction. And I've explored some of that elsewhere. And let me just point out the way in which inaction could be related to what I've just described. So basically, inaction says you have a field of processes, like physics or chemistry. You have some undifferentiated sort of thing. And within that field of processes, you end up with these closed networks of dependencies. This comes straight from autopoiesis, except it's generalized to the notion of autonomy. So these processes don't necessarily look like chemistry. And the components that trigger these processes don't necessarily look like molecules. Okay? But that generates an autonomous entity that emerges from a background dynamics of interacting things. And that autonomous entity defines an identity. It defines a thing whose existence is separate from the rest of the universe in which it's embedded. And by considering the causal arrows that flow across the interface between this thing and not this thing, you end up with a domain of interaction. Okay? And that domain of interaction specifies what in inaction is called significance. I've shown you that with the glider. There are certain configurations of the environment that, although they aren't intrinsically meaningful, are meaningful to a glider because they fall into particular classes that by a glider's very organization matter. They mean something to the glider. Okay, those are orange perturbations. They will cause me to make certain kinds of transitions, which will make me sensitive to certain future kinds of perturbations in a way that's different if they had been brown transitions. Okay, so these notions of autonomy, identity, domain of interaction, and significance in inaction, I think, could be fleshed out using extensions of some of these concepts that I've developed for the biology of cognition. That's the end. I'll take questions and/or I have some discussion topics when we're done with questions.
Thank you, Randy. My first comment is that because we have a lot of this here, probably most of them would agree with you that you should start with physics here. No, I don't know. So
it's not typically the way biology works, though.
So questions? Yeah. So sorry. So maybe this time let's state the name just so that we identify. Maybe. Okay.
Hello. Thank you for the talk. My name is Renata. I would like to have your insights about if it would be possible to define learning in the system, like what would be learning from the environment.
Yeah, that's a really interesting question. Before I answer it for this situation, I need to back up slightly. In my other brain-body environment systems work, where I'm dealing with bodies activated by muscles and by neural activity that drives those in closed loop interaction with the environment, I did some work where I evolved nervous systems that could engage in tasks that you would describe behaviorally as involving learning, but that did not have any synaptic plasticity. So the important point here is I have a view of learning which is basically just a matter of dynamics spread across multiple timescales rather than presupposing some particular mechanism of learning. Okay. And we analyzed those networks, and I showed exactly dynamically how they worked, but they did not involve anything like neuronal synaptic plasticity. So if learning behavior can be underwritten by just dynamics at multiple timescales, then sure, there's no reason why a more complicated agent than a glider couldn't have richer internal dynamics across multiple timescales, some of which underwrites learning behavior. I don't think the glider can do it because, as I emphasized, it's only got a single internal state, a binary, right? It's either a wedge or a rocket. Those two internal cells are either 0, 1 or 1, 0. And so the only thing it could learn basically is the class of environment perturbations that it may have just been exposed to. Because that one bit of information can't hold anymore. The only way you can take a one state dynamical system and get it to do more complicated things is by essentially restructuring the surrounding environment to serve as a richer memory, since you yourself can only remember one thing. But I don't see any reason why, if you had, some larger game of life entity with, maybe dozens of bits of internal states, therefore 2 to the dozens of possible values of that internal state, some of that might not operate. I mean, physically it all operates at the same time scale, but you can have longer and shorter paths of dependencies in that larger system. And so you can have dynamics on multiple time scales, some of which could underwrite learning type behavior, others of which could underwrite just moment to moment interaction with the environment.
Okay. More questions? No, yeah. You have 10 questions?
Hi, Randy. It's Daniel again. So
Hi.
I was very curious of the Umwelt part, right? I know that is is a provocation, but I wonder if you have some guess of what would be a good definition of Umwelt in the glider case.
Well, I think I would claim that I have calculated its Umwelt. Okay, it can only make these 6 distinctions. If you'll permit me some loose language, it only has 6 perceptual classes. The world looks to it like a blue thing, an orange thing, a green thing, and so on. That's the only distinction it can make. Okay, in the instant. Of course, it can make chains of contingent distinctions if it lives a longer life and makes a, say, blue, then brown, then gray, then blue distinction, right? But I would argue that that completely characterizes the glider's Umwelt. Now, if you're asking me some more philosophical, phenomenological question, what is it like to be a glider? I don't know. But what I can say is that while we see the game of life universe a certain way, the glider sees it a different way. And some other entity in the game of life would see it a different way. And furthermore, we can calculate those ways. In fact, I've shown we can calculate it from the underlying generalized organization of each of those entities. We can calculate their Umwelts spelled out in the particular way that I did. Whether or not that captures von Uexküll's full notion of an Umwelt, again, that's more of a philosophical question. But the idea that different organisms perceive the same objective environment differently is one I think that I've demonstrated gliders also do. And furthermore, like I said, I can calculate those perceptions, those distinctions that a glider makes, whereas we don't really do that in any formal way in biology.
I see. So do you think that actually we could, in principle, develop some semiotics for the gliders in this case, actually?
In principle, I mean, as I said, there's more to von Uexküll's notion than just how the world appears to one organism versus another. And all I'm claiming is that that first piece, that different organisms perceive the same situation in different ways, I think I've reproduced with the glider. Whether or not you could go from there, that's a really interesting question. I don't know enough about semiotics to say whether or not that makes sense, but it would be an interesting question for someone to look into.
Okay, great. Thank you.
Hi, my name is Facundo.
Hello.
In a more colloquial or relaxed discussion, I have some sort of journalist question that would be like, how does your view of the world changed since you started working on the Game of Life universe?
Well, I mean, working on the Game of Life in the context of Maturana and Varela's framework. So, I mean, there's all kinds of interesting things you can do about the Game of Life, like try to design entities that have certain properties like periods of oscillation, or answer questions about Garden of Eden configurations. Are there configurations that can only occur as an initial condition, never produced by any time evolution? These are things that people studied starting in the 70s. So that doesn't, the only thing that originally learning about the Game of Life did for me, as I imagine it did for everyone else that learned about it, is that it shows you how much complexity can arise from incredible simplicity. But in applying Maturana and Varela's framework to the Game of Life, so if I answer your question that way, I would say a lot. I discovered Maturana and Varela's framework as a PhD student. And I was a PhD student in computer science who had worked in AI and had basically come to the conclusion that classical approaches to AI were dead ends. And I was casting about for other ways of thinking about intelligence. And in reading a book called Understanding Computers and Cognition by Winograd and Flores, there was a chapter on Maturana and Varela. And I found that sketch of their ideas really interesting, really intriguing, largely because it was just so different from everything I had learned in computer science and classical AI. And I actually spent well over a year reading all of their original writings and organizing a reading group and so on. I really thought, this is interesting, this is interesting. But if anybody who's read that stuff knows, it's extremely difficult to understand. I always assumed that was because I was reading it in translation and that would be much clearer in the original Spanish. But I've had multiple Spanish speakers tell me, no, it's just as bad in the original Spanish. It's very, very complicated. You can kind of see that with some of the quotes that I threw up there. Okay. So I had this intuition that they were on the right track, that they had an interesting, different way of thinking about what an intelligent system is and how that intelligence, that cognition is grounded in its biology and so on and so forth. But it was all verbal. It was all, it's like, I sometimes call it wet tissue paper. It's the sort of thing that as you try to get more out of it, it just kind of falls apart in your hands. Okay. And what the Game of Life's application to those concepts did is it allowed me to flesh out a lot of interesting things that I think they hinted at. I think Maturana and Varela were on the right track, even though it was all verbal. But now you can slap down particular examples that say this is a different way of looking at biology, a different way of looking at cognition. And you don't have to puzzle out, parse very awkward, complicated sentences to see it. You can actually, we can compute, we can come together, let us calculate, right? I mean, we can actually lay these things down formally and calculate things about them. And that gives us, I think, new insights into biological questions, even though, as I keep stressing, this does not solve any particular biological concrete problem about what some particular organism will do in some particular situation. That was a long-winded answer, but that was my answer.
Okay, maybe we can move to the questions for the discussion. Okay, so let's see. Discussion question. How does a cognitive domain relate to cognition? Perceptual classes, Umwelt, and path toward an account of subjectivity. How generally applicable might these theories be? Okay, all the objects. What's missing from this toy model? Anyone
Yeah, some of
want to start?
this we've already touched on, but now we have another component of the model to discuss, the interaction component.
Yeah. Yeah.
Hello, my name is Lucas. I want
Hello.
to ask you about you. You mentioned that this game of life framework you apply it to an agent environment approach, but you mentioned that we have this brain body environment approach that is somehow more complex and adds another dynamics, and I think that it's very related to the idea of cognition, and I want you to talk a little about how can we relate these ideas with this framework and the game of life.
Yeah, so brain-body environment systems are a special case of agent environment systems, first of all, right? An agent doesn't have to have a brain. I mean, a cell is an agent, a biological individual that interacts with its environment. And all the stuff that I've just been describing could be applied to something like a cell, although the specifics only. A animal, which is where you really start thinking about brain-body environment systems, is more complicated. It tends to be larger. It's made of lots and lots of cells, it's not just a single cell, so it's a multicellular organism. And it's got specialized organ systems like nervous systems, but also digestive systems, and so on and so forth, musculoskeletal systems. So it's more complicated in that sense. But fundamentally, neither myself nor Maturana and Varela think it is a brain-body environment system is different in kind than a cell environment system. It's just that the complexity, the number of internal states that are available to this system, the variety of actions that system can undertake in its world, the richness of the perceptual access it has to that world, those are all astronomically larger. Okay. So that's my response to the first part of your question. The second part had to do with cognition. I have this interesting, so as Daniel mentioned, I've been in lots of different departments, including computer science and biology and electrical engineering and cognitive science. Currently, I reside in a cognitive science program and a neuroscience program, as well as informatics and computing. I don't believe in cognition in the following sense. I think cognition is not a natural kind, but kind of a ambiguous term. Usually, when people use the word cognition, they mean one of two things. And I've seen both of these among my cognitive science colleagues. On the one hand, cognition refers to just a set of very sophisticated kind of behavioral capacities that are typically only found in humans or perhaps higher primates, although that's changing a lot as the field of animal cognition has been progressing. Or, so it's a kind of behavior, it's a special, very human-like kind of behavior, or cognition refers to a particular kind of mechanism, which says that underlying these sophisticated kinds of behaviors must be something like the extraction and manipulation of representations of the world and of the agent's capabilities and so on. So it's either a kind of behavior or a kind of mechanism underlying that kind of behavior. Okay. I prefer strongly to just think in terms of behavior. And before you go and call me a behaviorist, which is the standard response to that, and I can reply to it if anybody wants to go that route, but I think the question is, for any living system, the kinds of behaviors in which it can engage and the mechanisms which underlie and support behaviors. You want to call them sophisticated enough to be human-like, or whatever mechanism they operate by, whether it's a cognitive process or not, I think are more specialized questions. And like I said, I don't see any consistency in the use of that term across fields, except that distinction between mechanisms versus behavior. So that's my take. So I don't think it's an interesting question. I don't really care whether you call anything the glider does cognitive or not. Mataran and Varela have a notion of cognition, which I explained to you based in terms of these cognitive domains, that uses the term cognition. Effectively, they license that use because they basically say that that cognitive domain is essentially the set of all possible things an autopoietic system can know about its environment. That's why they bring in cognition, because cognition is about knowing. Literally, the roots of the word are the act or process of knowing, is what cognition is derived from. I don't really care whether we call it cognition or not. That's why you mostly see me using the word behavior.
Yeah, I understand. A thing that I think about it is that this, when you have only an agent in an environment, we cannot talk about what information the environment sends to this agent, in the sense that everything that is in its boundary, it's information. But even when
Well,
we think about cells, we think that it have some kind of sensory that just will react to some variables. So it's like even cells are best fitted for the model of brain, body, and environment. And I think this internal part, this brain part, is where the cognition happens.
sure, but that doesn't require a nervous system, then you're saying. Because in a single cell, there is no nervous system. There are metabolic networks, there are chemical reaction networks that essentially play that role.
Yes.
Yeah, and I would argue that the glider does the same thing, albeit in a very, very simple way. It's not true that it reacts to the exact configuration of the cells that it experiences. I've shown you in some detail that it abstracts over that and basically only reacts to the distinction between these 6 classes. Everything within the class, every distinction within those classes, it ignores because it's in some sense constitutionally incapable of perceiving those distinctions. Okay, so it's also selectively interacting with some abstraction over the raw inputs it receives from the environment. Granted, in a very simple way, I'm not saying it's very cognitively interesting, but it's not trivial because it has that internal state that colors the way in which it responds to the same environmental configuration.
Yes, I can agree with you. Thank you.
Hi, it's Daniel here. So,
Hey, Daniel.
I have again a little bit of question about the Umwelt thing, because here you have a system where you have a full control. You know everything. You know the physics and everything. Right? But still, it's not very clear, and I think that's why you put the question. If we can understand the subjective point of view of a glider in this case, right? Well, so my question is that do you think that actually we have access to the subjective world of the glider, or actually even if you know all the physics, that's something that might be ill-defined actually.
I mean, it depends on what you mean by, I mean, you seem to be almost getting at the raw feels of experience, right? I have nothing to say about that. What I can say is that the glider, by its very constitution and in ways we can calculate mathematically, makes certain distinctions about its environment and fails to make other distinctions about its environment. So fundamentally, it can perceive, and therefore its behavior can be colored by the distinctions it can make, and it cannot be dependent on the distinctions that it's incapable of making. And in that sense, I've shown you basically the set of raw physical configurations is structured into these classes that derive from the glider's constitution. So, I mean, if you go back to Van Uxkel's sort of fanciful chapter where he draws worlds from the perspective of different organisms, if you're familiar with that, I can draw in a completely systematic, mathematically well-defined way what the world, what the universe looks like to a glider. And that can be completely derived just from its constitution, from its process dependency network, its organization. I don't know how to compute with raw feels. Okay, what does it feel like? What does it seem like to be a glider? But I can tell you definitively that a glider can never make a distinction, an instantaneous distinction between two completely different environment configurations that both fall into a Brown class. Okay. I can tell you that it can distinguish any configuration in a Brown class from any configuration in an orange class. I can, by chaining together these sequences of contingencies, I can show how it might be able to extract a distinction between Brown classes based on the sequence of things that it did. And by the way, with respect to the earlier question, I forgot to mention, I also do a lot of work in information theory. And I've done, you can calculate information quantities about the glider and about what it does and does not know about its environment at different points in time. Those are all mathematically perfectly well-defined things that you can calculate if you're interested in the currency of information rather than in the sort of dynamical structure of the system.
Thank you. So I think we can end now already. Yeah. Thank you so much, Randy, again.
Sure, happy to do it. Have a good rest of your workshop.
Thank you, Randy.